Hi everyone, welcome to the second recitation of AG codes. Unfortunately, there was some technical problem with the recording of today's class, so I'm recording it again. Before we begin, let me just mention that today we will upload problem set 0. It's not for submission, it includes several problems on rings and ideals. So those of you who want to practice the concept that we saw last time, it is recommended to take a look and solve as much as you can, but again, it's not for submission. One more thing that we will upload is the notes for the recitation, both this one and the last one. So both will be uploaded today. So let me remind you what we discussed last time. So let K be an algebraically closed field. So we mentioned last time that there is a bijection between the points in K to the n and the max spec, the set of maximal ideals of the polynomial ring K x1 to xn. So in fact, algebraic geometry is a whole field that translates geometry and commutative algebra, and this is just one example how to translate a geometric object, a point, to an algebraic object, an ideal, a maximal ideal in a polynomial ring. So what is the correspondence? Given a point A1 to AN in K to the n, we simply map it to the ideal n sub A, which is the ideal that is generated by the n linear polynomials x1 minus a1, x2 minus a2, xn minus an. So why is NA a maximal ideal at all? So we saw last time that we have the substitution homomorphism phi sub A. So it's a ring of homomorphism from kx1 to xn to k, which simply maps each polynomial fx1 to xn to its value at A. Substitute the point A. So it is easy to see that this is indeed a ring homomorphism, and it is surjective since each constant is mapped to itself. And I claimed last time that the kernel is exactly MA, this ideal. So I want to say a bit more about why is this true. So one of the inclusions is trivial. Which one? This one, that the MA is contained in the kernel, right? Since every element in MA is just some polynomial times xi minus ai, where I runs from 1 to n. And it's easy to see then that once we substitute the point A, everything vanishes. So this is clear. For the opposite direction, so suppose that f belongs to the kernel, we want to show that f belongs to the ideal, f of A. So for that, we can consider the Taylor expansion of f around the point A. So we know that we can write f as a sum of some constant times this product, where the sum of the exponent, runs from 0 to m, where m is the total degree of f. And now, obviously, if f is in the kernel, then f at A is 0. But what is f of A? When we substitute A, everything is cancelled except for the three coefficients, C0, 0, 0, 0. So C0 is 0, since this is the value. But then, that just means that we can begin the summation on 1. So each summand here belongs to the ideal MA, and obviously, so is the sum. So this shows that f belongs to MA. And in problem set 0, there is another way, more algebraic way to show it, to show this equality without using the Taylor expansion. So I encourage you to take a look at it. So again, since phi of A is surjective, we get by the first isomorphism theorem that the quotient of K, the polynomial ring modulo the kernel, is isomorphic to the image, which is K. And since this is a field, this is the maximal ideal. So in fact, MA is always a maximal ideal, even if K is non-algebraically closed. So this ideal of all the function that, in fact, the ideal of all the polynomial function that vanish at the point A is always maximal. But if we want the bijection, if we want bijection, we need to insist that K is algebraically closed. So we've already seen, for example, when n is 1, in Rx, the ideal x squared plus 1 is maximal, and of course it's not of this form, So, and that's okay because R is non-algebraically closed. So last time we showed the bijection when n is 1, and let me remind you, we in fact saw that the max spec of Kx is exactly the set of all the ideals generated by x minus a for some a in K. And we began to look at the case where n is 2. So we want to prove that there is a one-to-one correspondence between the points in the plane, K2, and the max spec of Kx1. And again, what is the correspondence? Given a point, we want to map it to the ideal of this form, x minus a, y minus b, ideal generated by these two functions. So let's see. So in order to show this, we need the 2 or 3 claims, and then we will conclude. So let me begin with the first one, which we already stated last time. So let F so K is a field which is algebraically closed, but F is just a field, not necessarily algebraically closed. So let F be a bivariate polynomial over some field F, a non-constant. Then the ideal generated by F is not maximal. So it is clear that all these ideas are maximal, but we want to show that this map is injective and surjective. Every element in the max spec is indeed of this form for some A. Then the first step is to show that the ideal that is generated by F is not maximal. In other words, maximal ideals are not principal. Okay, so our first step will be to show that an ideal that is generated by a single non-constant polynomial cannot be maximal. So prove. So let me remind you, last time we defined the set ZF, the curve that is defined by the polynomial f, and for us, it is the set of all the points in f bar times f bar, where f bar is the algebraic closure of f, all the points such that FAB is 0. So here we take f bar. We can also take some other field. We can take f times f or some other field, and of course it will change the curve that we obtain. But for today, we'll only consider this curve. What we showed last time is that this set ZF is non-empty, and in fact is infinite. in particular, there exists AB in ZF. So these things we showed last time. So we have a point on the curve. And what can we do? So consider the ideal that is generated by x minus a, y minus b. So this is ideal in which ring? Note that a and b belong to f bar, so not necessarily fxy, but f bar xy. So this is an ideal, and in fact a maximal ideal, right? Because m bar is exactly the kernel of phi of AB, right? So m bar is exactly the kernel of the substitution homomorphism which substitute the point AB. So it is maximal ideal, and in particular, it is a proper ideal. And let M, okay. So, but we want to work in this ring, so let's take the intersection of M bar with fxy. So we consider the intersection, and it's not hard to show that this is an ideal of fxy. So it's not hard to verify that this is indeed an ideal, and in fact a proper ideal, right? Because M bar is proper, so for example 1 does not belong to M bar, so 1 does not belong here, so it's a proper ideal. Also here. And what can we say? So what is F? AB is a point on the curve that is defined by F, that is FAB is 0. So in other words, the function F belongs to the kernel of PAB. When we substitute AB, we get 0. But the kernel is exactly M bar. But F, not only belongs to M bar, it also belongs to fxy. So it belongs to both this and that. Hence, F belongs to M. So F belongs to M. In particular, the ideal that is generated by F is contained in M, right? Because this is an ideal which contains F, and this is the smallest ideal that contains F. So obviously we have this inclusion. And now we can separate two cases. So case 1 is when the ideal generated by F is strictly contained in M. Then in this case, I claim that we are done, because obviously, if it's strictly included in a proper ideal, then it cannot be maximal. So this case is done. It remains to prove in case F is equal to M. So suppose that we have this equality here. Then what can we say? So we call it A, the first coordinate of the point, belongs to F bar. F bar, the algebraic closure, is in particular an algebraic extension of F. So in particular, A is algebraic over F. So let BA in Fx be the minimal polynomial of A over F. So what is the minimal polynomial? The minimal polynomial of A, it's the unique monic polynomial of smallest degree, such that A is the root of this polynomial. So such a polynomial exists and it is unique. So for example, if A is I, then over C, what is the minimal polynomial? X minus I. It's a polynomial in Cx, monic of minimal degree such that I is a root. But over R, it's x squared plus 1. Because this is not a polynomial in Rx. So we have to go to this point. Okay. Now, since A is a root of P of A, it follows that the polynomial x minus A divides P of A. Right? If A is a root of a polynomial, then x minus A divides this polynomial, where? In F bar x. Because remember, A is in F bar, not necessarily in A. So in particular, we get that P of A belongs to the ideal that is generated by x minus A, and obviously I can add y minus b as an ideal in F bar xy. Right? Because PA is just some polynomial in F bar x times x minus A. So obviously it belongs here, but this is exactly n bar. In addition, since it's the minimal polynomial over F, we also know that PA belongs to F of x. So obviously to F of xy. So P of A belongs to M bar and fxy, so it belongs to the intersection, which is M. PA belongs to M. Because it belongs both to fxy and to M bar. And since we're in case 2, we assume that M is exactly the ideal generated by F. Okay, so what does it mean? That means, and this ideal generated where? In fxy, not F bar. Right, so this is ideal of the ring fxy. So it follows that hence simply f times g for some g in fxy. Right, so the fact that PA belongs to this ideal means exactly that PA is f times g for some g in the ring. But now, let me remind you that the minimal polynomial, one can show that it is an irreducible polynomial. Maybe before that, P of A belongs to fx, right? And these two belongs to fxy, but if the product is in fx, then both must be in fx as well, right? Since the degree of y here is 0, so it must be that both f and g do not include y. And f is reducible in fx, since it's a minimal polynomial, and the minimal polynomial is always irreducible. That means that if we can factor it to f times g, then one of these must be a unit. So and the units in fx are the constants, non-zero constants. But f, remember, we started with f, a non-constant polynomial. So f is not constant, so g must be constant. So a irreducible implies g is constant. So the ideal that is generated by f is just the ideal that is generated by P of A. So what should we do next? We should consider the quotient fxy mod the ideal generated by f, which is the same as fxy mod the ideal generated by P of A. But this is a univariate polynomial. It only contains x and not y. So it's not hard to show. In fact, it's a nice exercise to show that it's isomorphic to what? To the quotient fx mod P of A y. So why is this true? So I will leave it to you as an exercise, but one way to show it is to give a surjective ring homomorphism from fxy to the right-hand side to show that it is surjective and that this is its kernel. And then again use the isomorphism theorem. So I leave it to you. But now, what do we get? So we get a polynomial ring, in fact, over a field, because this one is irreducible, so this is maximal, so this is a field, but the polynomial ring over a field is not a field. So it follows that the ideal that is generated by f is not maximal. Okay, so with this we are done. And let me just make one comment about it. So in fact, what is the full truth? So we began with m bar, which was the maximal ideal in f bar xy, and then we took the intersection of m bar with fxy, and we claimed it is a proper ideal of this ring. And in fact, you can show that m is a maximal ideal of this ring. So we didn't do it, but we could have done it. One way to show it is to see that if you take phi of AB and restrict it from this domain to this domain, then the kernel is this. And then play again with the isomorphism theorem to conclude that this is a maximal ideal. So in fact, when we consider the two cases, M is indeed a maximal ideal. So, and F is not. We just proved that F is not. So this case cannot happen. So what is really happening here is that M is always maximal and F is always strictly contained and not maximal. But never mind, just a comment. Okay, so let's continue. The second claim that we will need is the following. So let A be a UFD, unique factorization domain. So what is a UFD, a unique factorization domain? It's a domain in which every element A can be factored to irreducible elements. Every element is a product of some irreducible elements, essentially in a unique way. So if A is the product of P1 to PR, where all these are irreducible, and it's also the product of Q1 to Qn, where all of those are irreducible. Then R and M are equal, and up to permutation of the indices and maybe multiplication by a unit, P and all the P's and the Q's are the same. So for example, in Z, 3 times 2 and minus 2 times minus 3 are essentially the same, because up to a multiplication by a minus 1, which is a unit, and changing the order, it is the same. So the claim is that A is a UFD, and let M be a maximal ideal in AY. So soon we will take A to be Kx, the ring of polynomials in one variable x, and then AY is Kxy. Then if M is not, so if M is not principal, if M is not generated by a single element, then M then the intersection of M and A is non-zero. So again, we have A UFD, and we take consider the polynomial in AY and take a maximal ideal M. Then if M is not principal, then M intersection A is non-zero. So one corollary, we can take the UFD Kx, which is a UFD, and then it follows that if M is a maximal ideal of Kxy, right? Because A of y is Kxy, which is isomorphic to Kxy, and if M is maximal, and if it is not principal, but we already saw by claim 1 that a principal ideal in Kxy cannot be maximal. So if it is maximal, then it is not principal, then we can conclude that M intersection with A, with Kx, is non-zero. Okay, so again, if we take a maximal ideal of this ring, then there must be some polynomial in Kx, which is non-zero, that sits in N. Okay. So maybe before we give the proof of claim 2, let's see why now we can finish. So the third claim is let M be a maximal ideal of Kxy. So let M be some maximal ideal of this ring. Then we can conclude that M is the form x minus A, y minus B for some AB. For some point AB in case 12. Proof. So first, the corollary says that if M is a maximal ideal, then its intersection is non-zero. So let P be this intersection. What can we say about P? Well, it's easy to check that it is an ideal of Kx. So I will leave it to check. We also know that it is non-zero by the corollary. And we also know, moreover, P is non-zero and is prime. So why is it prime ideal? So one way, just to check the definition. So suppose that Fg in Kx are such that Fg belongs to P, and we want to show that either F belongs to P or G belongs to P. This will establish that P is a prime ideal. So for every F and G in the ring, if the product is in P, then one of them must be in P. And why is that? So obviously, both of them are in Kx, and their product is in P, so their product is in M. But M is maximal. In particular, it is prime. So if Fg belongs to M, then F belongs to M or G belongs to M. So one of them, at least one of them, belongs to the intersection, so it is indeed a prime ideal. But what are the prime ideals of Kx? So last time we saw that there is the zero ideal is prime, but P is non-zero. And the other are ideals that are generated by x minus a for some a. So remember last time we saw that the spec of Kx, the set of prime ideals in Kx, are exactly the set of all the ideals of this form plus the zero.